Hi everyone. This is the talk I gave at the Asian European workshop on SUN physics in condensed matter and ultra-cold atoms. This is a workshop that was organized by Professor Yamada, Professor George Jackley, Professor Frederick Miller, and Professor Carol Pink. That was one of these invited speakers. So I will talk about intertwining frustration and SUN symmetry in frustrated lattices. So this the outline. So I will first give a rather brief introduction and some background about SUN symmetries and models. And second, I will talk about frustrations due to strong charge fluctuations and combined with SUN symmetry. Later, I will discuss about chiral spin liquids and competing orders in triangle lattice SUN model insulators. And these talks are covering two papers of us. This is in blue color. So the second one and third one. I probably don't have time to talk about the third one, this one, which is about the honeycomb lattice SUN model. So this work is in collaboration with my former graduate student Yonghao Gao and my current graduate student who just defended last month. He defended his PhD thesis, Shuping Yao. And this work, which I probably don't have time to present, is a work collaboration with Shuping Yao and another graduate student, Rui Luo. And part of the work was also in collaboration with my former collaborator, Kaden Hazzard, who is I think associate professor at Rice University, and Maria Ray and Mike Hermele, both are faculties at University of Colorado Boulder. So where do we expect SUN symmetries? There are multiple places one can think about approximate, the system is approximate to SUN symmetries in both condensed matter systems and in ultra-cold atoms. First, historically, was this Komsky model. I think it was proposed much earlier than in the 1970s, and it was summarized in a beautiful review paper in 1982 by Kugel and Komsky. So because of the involvement, this is a spin orbital model. So there are orbital degrees of freedom on top of spin degrees of freedom. It's a super exchange model for spin and orbital degrees of freedom model insulator in model insulator. So typically, because of this involvement of orbital degrees of freedom, these models are highly anisotropic because orbital has orientations. So if you want to establish high symmetry such as SUN symmetry, you need to do some amount of fine tuning to tune parameters so such that system can have SUN symmetries. So generically, we don't expect SUN symmetry, but SUN high symmetry can be a very good starting point to study the property of the system, and then let's go away from this high symmetry point and see what other property can persist, or some of the property can be lost if you turn off the high symmetry, if you get away from the high symmetry. So there's more concretely, this compound, this is not a spin orbital model. So this barium copper antimony oxide. So it's more like a multi-layered triangle system, I think. And so copper is spin 1/2. So because this copper and antimony has this interside disorder, so people model that as effective spin 1/2 degrees of freedom. But really, because this copper and antimony is more like a drum bell type of degrees of freedom, this is more like a quench disorder rather than a dynamic degrees of freedom. So whether it has this SUN n equal to 4, SU4 symmetry or not, it's not really that clear because of this more like quenched degrees of freedom. So people propose, our chairman, I think most of the chairman, Ishikawa, Yamada, and George. So they propose a realization of so-called J equal to 3/2 spin orbit entangled local moments in a D1 transition model oxide, such as the cadmium trichloride. Well, I was also involved in this proposal of D1 J equals 3/2 in this double perovskites more than 10 years ago. Yeah. So So again, because of this because of this involvement of orbital degree of freedom, these models are also highly anisotropic. So if you want to establish SU4, in this case, because JU3 have involved four states, so you would think the system can have SU4 symmetry. So if you want to establish SU4 symmetry, you also require some amount of fine tuning. So it's not exactly SU4 symmetry. So under certain approximation by Yamada, Jack, George, and Masaki, so they propose the conium trichloride in certain limits can have this SU4 symmetry. Yeah. So more recently, because of the surge of twisted Mori systems, the people propose high symmetries such as SU4, SU8, etc. In this system because of the involvement of multiple flavors of degree of freedom, such as spin, valley, orbitals, etc. Yeah. So these are all condensed matter systems, right? So cold atom system is in some sense, in some aspects, like ouch-cold atoms can be a little bit more clean in some sense. This is the first work by Konju and his former collaborators working on these alkaline atoms. So because of fermion statistics and contact interaction, the wave function has to be, the special wave function has to be symmetrized in order to establish a contact interaction, because the alkaline atom that was studied are all fermions. So that means the orbital the spin part of the wave function has to be antisymmetric. So there constrain the number of contact interactions in this alkaline atoms on optical lattices. In the end, Konju and his collaborator were able to show the model the interacting Hubbard model would have exact SPN symmetry. SPN symmetry. So with some amount of fine tuning, but because there are only two parameters, interaction parameter for these alkaline atoms, if you tune the coupling to certain relation, you can establish exact SU4 symmetry. So that was more or less the precursor of high symmetries in ultra-cold atom systems. Later, people studied SUN symmetries in alkaline earth atoms. I was initiated by a couple of people. That was my former collaborators like Anna Maria Ray and Jun Ye, Mike Hermele. In Japan, this Takahashi's experimental group on ytterbium atoms. That was an alkaline earth-like atom. Yeah. So Kaden Hazzard. So over there, because of nuclear spin. So nuclei is very small when the atoms scatter each other. So the scan length is much larger than the nuclei. So in the end, scan length is independent from the nuclear spin states. In the results, the nuclear spin state become a symmetry. And if you have like for ytterbium, you get a nuclear spin I equal to 5 halves. So then you get a 6 states. You get a SU6 symmetry, right? If you have nuclear spin 9 half, you would have SU10 symmetry. Strontium has a nuclear spin. The common isotope of strontium, strontium 87, has a nuclear spin I equal to 9 half. So in principle, you would have SU10 symmetry. So it's kind of illuminating to think about some mutual feedback between condensed matter systems and this ultra-cold atom systems. So it turns out that these what has been used in condensed matter like helium-3, so-called Pomerleauchik cooling, because of the presence of nuclear spin of because of the spin degree of freedom of the helium-3 atoms, people can realize this Pomerleauchik effect because of the entropy carried by the spin degree of freedom. So you can do Pomerleauchik cooling So making use of this large enhanced spin entropy, internal symmetry from the spin degree of freedom, one can realize, one can carry out polymerological cooling for these SUN atoms. That was demonstrated by Professor Takahashi for ytterbium SU6 and show the presence of motor instead for ytterbium atoms on optical lattices. Later, people also discovered polymerological effect in this Morris system due to the presence of so-called spin and vary, high number of internal entropies due to the spin and vary orbitals. And so that was work I think last year by Princeton group and Santa Barbara group. So what's interesting about this SUN SUN models or SUN degree of freedom? Why we are working on that? So to answer this question, one can make a comparison between so-called large S limit for SU2 spins in condensed matter system and the larger limit for for SUN degree of freedom. So we know when for SU2 spin, in solid state system, if the spin is large, the spin quantum number is large, there are more states. But the system actually behave more classically because the modeling Hamiltonian is most often is a Heisenberg or Ising or XY like models. So if you apply this model, this Hamiltonian to a state, imagine a spin state is in a fully polarized state here, S equal to S plus S. If you apply the Hamiltonian once, you can only tunnel at most tunnel the spin state by you change the spin quantum number by 1, right? You cannot access the other state unless you apply Hamiltonian multiple times. In comparison, for SUN spins, all these generators for SUN symmetry all appear in the Hamiltonian. So if you apply Hamiltonian once, you will allow the spin state to tunnel from 1 to all these rest and -1 states, right? With almost a similar amount of tunneling probability, right? So that means the spin states are more delocalized in the physical Hilbert space, right? It's more delocalized. It's easy to tunnel from one to the other. In comparison, for this larger S limit, the spin state is a lot more localized. It localized close to this fully polarized state. So imagine the system will develop some kind of magnetic order. So the quantum fluctuation around this magnetic order is rather limited because of this limited fluctuation here. But for this SUN spins, the quantum fluctuation is very strong. The spin state is much more delocalized within its own physical Hilbert space. As a result of this enhanced quantum fluctuation, as a result of this strong delocalization in the physical Hilbert space, one could stabilize more exotic and quantum mechanical phases with these SUN spins, right? So that's part of the motivation, or one of the strong motivation why we work on SUN degree of freedom and models, right? So this is, in fact, this kind of comparison was already being given in the more ideal, kind of limiting condensed matter system by Nick Rui and Sechdev in 1990s, where they tried to understand the interacting spins on the square lattice. One can do, conventionally, one can do larger S expansion and larger N expansion, right? So these are two different expansions. In a large S limit, basically the spin became more and more classically. The system stabilized conventional magnetic order and their order. But in contrast, in this larger N limit, if you have SUN symmetries, the quantum fluctuation is much more enhanced. So you get a more exotic states. So these are two different kind of limits, right? So yeah. So this is a more physical explanation of why SUN symmetry, SUN models, or SUN degrees of freedoms are more attractive to us. Yeah. So in fact, even on unfrustrated lattices, such as square lattice. If you place SUN, degree of freedom on the square lattice, interact with the SUN Heisenberg model, for example, the system is already frustrated, right? So it was shown by Michael Hermele and Vicky Garrett and Maria Ray with self-consistent stable fermion treatment. They show in a larger limit. So M is the number of particles per site. The most stable experimental limit would be M equal to 1, so 1 particle per site. So this is the most stable one because of the reduction of cerebral loss that prevails in ultra-cold atom systems. So if you have M equal to 1, so when this number of particles, this SUN K is basically N. So when N is small, you get you tend to ferromagnetic order of some sort. When N become large, quantum fluctuation becomes strong. And in the end calculation, they show when you establish so-called chiral spin liquids, right? It's a exotic topological chiral abelian topological order, right? With a fractional statistics. So in fact, the numerical calculation do support a more unconventional phases when N become large, right? So N equals 3. So numerical calculation by our chair, Federico Mira and Carl Planck and Andreas Lochley, they found the so-called 3-sublet stripe order. And for SU4, you get a colored VBS because this VBS has flavors. It's not a spin singlet. It's not a SU4 singlet because only 2 sides are involved. For other higher ends, more exotic states can emerge, right? So these are supported by different kind of numerical simulations. As we know, all these numerical calculations have its own limitation. So I don't think there is a consensus on many of these results now. Yeah. But the general belief is when N is large enough, the quantum fluctuation become very, very strong, and the more exotic quantum phases can be stabilized. Yeah. So what's chiral spin liquid that was prevailed and it was found in these calculations. So in Michael Hermele's calculation, when N is greater than or equal than 5 on the square lattice, one can establish a chiral spin liquid with spontaneous broken time symmetry and with spontaneous generation of this U1 gauge flux, which is 2 pi over N on each placket, right? So at the mean field level, the spin-ons, the fermionic spin-ons, so experience this this emergent U1 gauge flux and from lambda level and field lowest lambda levels. So there will be chiral edge modes propagating on the edge, right? So the system is fully gapped and supporting anionic-like excitations with fractional statistics. So they are topological protected edge states, and the edge will describe by SUN level 1, WZW model, right? So there can be some experimental issues. How do we cool the system down to the spin liquid regime? If there is a chiral spin liquid, so how do we do the braiding to confirm the existence of anions? How do we actually measure the edge states? This is not a condensed matter system. So we put the cold atom into a harmonic trap. The edge is not that sharp. So how does one actually measure the edge states? So to as I said in the beginning, in the introduction, there can be an interesting mutual feedback between condensed matter system and ultra-cold atom systems. So I want to illustrate this point a little bit further. So this is kind of inspired by this early work on the triangle lattice Hubbard model. So in the weak motor regime. So triangle lattice Hubbard model. So we know, like in a strong correlation limit when U is large, so the effect model will be Heisenberg model, and the ground state is a trivial 120 degree magnetic order, so-called root 3 magnetic order. But if you go to the weak motor regime, when the U becomes a little bit small, it becomes smaller and smaller, but still large enough to to localize the charge to obtain to establish a motor insulator. So in this regime, because the charge gap is become small, so the charge fluctuation is become strong. So when you do perturbation theory to obtain the effective interaction between the local moments, the charge is still localized. The electron is still localized, but it's quasi, quasi determined in some people's language. Then still, there can be significant charge fluctuation that generates so-called ring exchange, so-called four-side ring exchange. In such a regime, this 120-degree magnetic order is believed to be melted by the strong fluctuation due to charge fluctuations. So the proposal is this intermediate weak motor regime state is a spin liquid, spin on surface spin liquid. So nevertheless, some new work says this can be a chiral spin liquid. So if people ask me, I will get into this question why this new work by Michael Zelatev and Joe Moore from Berkeley, they're doing DMRG, later they have a mean field calculation support to understand why it's a chiral spin liquid. So the physical mechanism for this weak motor insulated spin liquid was this so-called four-sided ring exchange that competes with this near stable Heisenberg model. So one can borrow this idea from this triangle lattice Hubbard model in this organic triangle spin liquid systems to this our SUN models. Now, just imagine you create optical lattice with square optical lattice and load with alkaline earth atoms, and if you clarify interaction, the interaction does not necessarily to be in the strong motor regime, right? You can imagine the interaction is in the weak motor regime. So we think about we propose this kind of effective Hubbard model. So with atom hopping on the optical lattices at the same time with on-site Hubbard interaction, we make sure the filling is so 1/n filling, basically one particle on each side on average. In addition, we introduced this synthetic gauge flux. This flux is 2π/n flux for two plaquettes, or 0. So either we put the 2π/n flux per plaquette, or we turn off the synthetic gauge flux, so with and without the synthetic gauge flux. So in a strong U limit, when you do perturbation theory, where the atom is fully localized, the effective model is always a Heisenberg model, SUN Heisenberg model, regardless of whether there is a flux or there is no flux, right? Because you do perturbation theory, the atoms hopping back and forth, right? So the first, hopping will be cancelled out. So the nearest neighbor Silk exchange will be non-chiral. But if you go to high order, if you go to like some kind of ring exchange, the one with synthetic gauge flux will pick up a first factor to pick up this chiral phase, and pick up this flux from the higher order perturbation theory, right? So this is the Hubbard model. So we're doing this. We try to understand the property. The first diagram, the transition from non-interacting or weakly interacting metallic-like state really can be gapped to a regime, to a motor insulating regime where the particles the atoms are localized and form a motor insulating state. I want to understand this kind of SUN version of the Mott transition, right? So this is established by so-called step rotor approach, and one borrow from this step rotor approximation, step rotor kind of factorization in the for the SU2 Hubbard model to SUN Hubbard model here, right? So one separated the electron operator into a bosonic charged rotor and a fermionic spinon, right? So when the charged rotor is uncondensed, this is the system corresponding to weakly interacting, metallic-like state. If you have flux, that is the system is in a quantum Hall, integer quantum Hall state. Without the magnetic flux here, without the synthetic gauge flux, it's a metallic state. Yeah. So when this charge loader is condensed, yeah. So when this charge loader is uncondensed, the system enter a model incident state. And it depends on nature of the fermionic spinon sector. Depend on the nature of the spin sector. The system can be in a deconfined phase or can also be a confined phase. So we'll check for many different states here. So this is the first diagram for the SUN Hubbard model without the synthetic gauge flux, and the SUN Hubbard model with the synthetic gauge flux. So one finds that we know in the large U limit the system is described by Hazzard model. So we know the ground state in this larger self-consistent calculation was found to be a chiral spin liquid, right? So this calculation should be consistent with this large U limit chiral spin liquid. So this Hazzard model was at one point in a strong U limit. It is really in a strong U limit. If we go to intermediate U limit, because of this chiral spin liquid is a robust state matter. If you just decrease the U a little bit, decrease the U, the state is quite robust. Actually persists into the intermediate U limit. So even in the case of without the gauge flux, it persisted to this regime. If you have synthetic gauge flux, because the flux is tuned in such a way, it's identical to the emergent U1 gauge flux in the strong U limit in the Heisenberg model, right? So that means the chiral spin could even persist down to the actual mode transition, right? So then the direct transition from chiral spin to a integer quantum Hall state. Yeah. In contrast, without the gauge flux, so there is this so-called spin-on-forming surface spin liquid emerge in the intermediate U limit, intermediate U regime, and become a forming liquid metal in the weak U in the weak U uncorrelated, weakly correlated regime. Right? For n equals 3 and 4, I have to say so the system was found to be in a VBS state when U become large, right? Instead of chiral spin liquid, except that for the one with gauge flux, the chiral spin liquid is more energetically favorable in the weakly correlated regime here. So that means with the large with the presence of this synthetic gauge flux, chiral spin liquid occupies a much larger regions of the phase diagram, right? If you look at this phase diagram, there's a huge region of this blue area is being chiral spin liquid, right? In compare with the one without gauge flux, which is here. Moreover, even without even in the case of without gauge flux, there is an interesting of spin-on-forming surface, which is also a very exotic quantum physics. It's U1 quantum spin with a spin-on-forming surface. Yeah. The other thing I should mention is in the numeric calculation by our chair Ferric Miller and his collaborators, they find that when for SU3, one have this kind of SU3, one have this kind of 3 stabilized magnetic order. So if the 3 stabilized order appears in some regions here, then can be a direct transition from chiral spin liquid to the 3 stabilized magnetic order. So the understanding of this transition is a very interesting problem. because this is the transition between an intrinsic topological order state to a conventional magnetic order state, right? So it's essential to understand this transition when to describe this transition. When essentially need to condense the anions, condense the anions in the chiral spin liquid to destroy the chiral abelian topological order. At the same time, induce the translational symmetry breaking in the 3 sublattice magnetic order and induce the magnetism, right? So that's the that's the interesting part of this transition. Yeah. So what's the advantage for working in this so-called intermediate U regime, right? So intermediate U, brings actual fluctuations. Now we know, like in the strong U limit, when the system is described by the Heisenberg model, the fluctuation is very strong. Is very strong. Even we reduce U, the charge fluctuation becomes strong. The fluctuation become even stronger. So there is the twice level, the double fluctuation. One due to the intrinsic fluctuation due to the SUN symmetry, the other is due to this charge fluctuation, which in both of them enhance quantum fluctuation, right? Yeah. So moreover, in the intermediate limit, the gap of the anions in the chiral spin liquid become large, become enhanced, become maybe a factor of 3, from 0.1 to 0.3 here. So that means the temperature, the temperature requirement to observe the property of chiral spin liquid or observe chiral spin liquid phase can be less stringent, or even on top of the SUN symmetry could help with the cooling, basically due to the large entropy here. This is what's called a polarical cooling, right? Other favorable aspect of the synthetic gauge flux is the absence of the intermediate spin-on-forming surface state, right? And all the transitions are continuous in the mean field, so all the transitions here are continuous. So one can adiabatically, wrap the interaction from the weak U to the strong U, without the gauge flux, compared to the one without gauge flux. So the gauge field itself introduces further complications, such as complex band structure, even in the weakly interacting regime, right? So determine the optical preparation is beyond the scope here. However, even if the cooling temperature is below the chiral spin liquid gap, is outside the current experimental reach, it's still possible that certain features associated with the chiral spin liquid may still be visible experimentally. Yeah. So what are the methods to detect the chiral spin liquid and the spin-on-forming surface, right? So the presence of time symmetry breaking at final temperature is a consequence of chiral spin liquid. If you don't have synthetic gauge flux, the system has time symmetry, but chiral spin liquid does not have time symmetry. Time symmetry is ion symmetry. It should have a final temperature phase transition, right? So this will be one of these sharp. You should have a thermodynamic features. Yeah, to detect the chiral spin liquid, Hermele and Vicari actually suggested to probe two characteristic properties of topological phases, looking for topological protected chiral edge states, chiral edge current, introduce weak attractive potential, just try to create some defect bound the anion excitations, and try to braid or interfere these defect bounded quality particles. Yeah. So to detect the spin-on-forming surface, one can perform a spin-dependent, so-called spin-dependent Bloch spectroscopy to detect two spin-on continuum in a dynamic spin structure factor, and the most basic signatures of this exotic nature of this phase is the lack of order and the existence of gapless excitations. Yeah. So the detailed structure of these excitations, spin-on-forming surface, can be revealed by considering more interesting structure of the spectrum. So with that, let me switch gear to triangle lattice SUN, Heisenberg model. So this model is become more and more experimental relevant because of this emergence of this twisted bilateral graphene, twisted module system, which presumably can be described by SUN Heisenberg model on triangle lattice. Yeah. So this early work by Frederick Miller and his collaborators, Andreas Lochley and Carl Pink, and also a group in Japan. So it's more than 1.5 decades ago. The reason people work on that is because of this spin 1 material, nickel gadolinium sulfur, was proposed by Nakatsuchi group 2003-2004 as a candidate for two-dimensional spin liquid because it has a very robust T squared in special heat and doesn't really order. The physics over there is more like gassy, gauge glass like kind of T square is more like a pseudo ghoststone, like a Hubbard mode. It's ghoststone mode, Hubbard type of mode. Yeah. But anyway, around that time, people proposed the model of the system is some kind of Heisenberg biquadratic type of biquadratic interactions for any, if the sign of the biquadratic interaction is magnetic with some fine tuning, one can have SU3 symmetry, and the numerical calculations find the SU3 has a more model supports so-called 3 sublattice magnetic order. Yeah. So that was 2006. It was 15 years ago. Later, I think last year or the year before last, Annie and Lucia Savary and the Unbalance, they work on SU4 as a model on the triangle lattice. This is a half filling, 2 particles per side. So they find the VBL state with root 12 unit cell. And Annie and others, Chen Ke-Xu, Chao Mingjian, and Boer. So they with 1 particle per side. So this fundamental representation with DMRG, both of them are DMRG on cylindrical geometry. They find a gapless spin liquid, U1 spin liquid with spin on formal surface. Another set of people, Professor Zhou Yi, Professor Tao Hong Tu, and their students and postdocs, they find a critical striving state. It's more like a nematic spin on formal surface spin liquid. It broke a lattice rotational symmetry, but the system still gapless. Yeah. So this is work by Andreas Lochley and Fedor Miller and Carl Pink. They look at the SUN Hubbard model with synthetic gauge flux on the triangle lattice. They find a large presence of large region of the first diagram is the SUN and chiral spin liquid if you have a non-zero flux on the triangle lattice, so you can stabilize chiral spin liquid. So here we are explore SUN Heisenberg model by varying n with a Brikasov fermion approach. So to see what's the ground state. So this the method here we are using is a very common method. It's a self-consistent large n approach. So in this approach, one express the SUN operator as a bilinear of Brikasov fermion under the constraint under the physical constraint of one fermion per side, right? So this larger approximate larger approach differs fundamentally from the original larger extension of SU2 spins by Sachdev and Reed in 1990s. So in Sachdev and Reed context, the filling is always fixed to be 1/2. So two sides, it's always 2 sides that form a spin singlet, even with large n, right? Even with large n. So the particle number over there will be n/2 per site, right? Two sides form a spin singlet. So in comparison here, we fixed to be one particle per site. So we need just need n side. We need still need n sides to form a spin singlet. That's the key. That's the key difference. Yeah. So the method is a self-consistent large n calculation. So one does this partition function expressed into particles and introduce this auxiliary forming bilinear between two sides, right? To do this decoupling and obtain a mean field large n. In a large n limit, the mean field Hamiltonian is established here. We need to self-consistently find this bond operator chi and the chemical potential. So instead of putting a chemical potential on average to make sure the feeding is this is Hilbert space enforcement is being enforced on average, we introduce a chemical potential for each site and make sure the Hilbert space constraint is being enforced on every site instead of on average. So we need to determine the chemical potential self-consistently for each site rather than on average. So to do that, this is the algorithm introduced by Hermele and Gary in their work. So Anna Maria in their work. So essentially, in each of the calculation, one evaluate the deviation of the of this particle number per site, right? So and find the deviation away from this one particle per site. So then we need to adjust the chemical potential per site, adjust this chemical potential mu per site, and make sure it correct this give you the right Hilbert space enforcement of one particle per site. This is established by finding the density correlation function, right? By finding the response function, essentially the compressibility, right? Essentially compressibility, and find the inverse of the compressibility, and then you adjust your chemical potential for each site and make sure the one particle per site is being enforced. So this is very important. If you do not do that, if you impose the Hilbert space constraint on average, you set mu r equal to mu on each side, for every side. So then you do not get the right answer. You cannot obtain the right state of the right ground state. Yeah. So this is the algorithm that was established earlier. So this mean field theory turns out it has this beautiful result, beautiful so-called lower energy bound that was established by Rokhsar in the old days of when Rokhsar worked on this mean field theory. He found that this mean field theory has a lower energy bound, right? So the lower energy bound is given, one can extend the Rokhsar result for SUN models, SUN Heisenberg model with 1/n finite, and the lower bound is given as this. I think it was established in Mike Hermele's work. So it turns out that for n equal to 2 and n equal to 3, one can use this diamond covering. SUN for SU2, this two-sided form a singlet. For SU3, a three-sided form a singlet. So one can use this so-called diamond cluster cover valence cluster states to saturate this lower bound. Once this lower bound is saturated, one firmly establishes the presence of this mean field ground state. But we know when n is small, we don't know when n is small, so this calculation is not this mean field larger approximation is not going to be quite reliable. So when n equal to 2, n equal to 3, especially when n equal to 2, the ground state is 100-degree magnetic order. One cannot trust this. One cannot firmly trust this calculation. Yeah. when one is large, one can probably say something good about this large N calculation. So this is the list of the ground state energy and the lowest competing states for different N's. Particular for N equal to 4, so the ground state is found to be this so-called placket state. It's a four-sided placket. Remember, this is one particle per side. We need the four side to form a spin singlet, SU4 singlet. And the competing state, is a stripe state. In the stripe state, in a sense, the system breaks rotational symmetry. So the bond it has a stronger, this bond parameter chi, and this gray color has a weaker, has smaller chi amplitude, and this is the intermediate one. So it breaks the rotational symmetry and the translinear symmetry. It's a gapless state, right? It turns out that this in our calculation, this is the lowest energy competing state, and in Annie's calculation, DMRG and Professor Zoe and Professor Tuan Hao's calculation seem to support this stripe gapless state as the ground state. Yeah, we'll see. Annie is giving a talk tomorrow. We'll see her explanation. Yeah. So for N equal to 5, the ground state in field ground state is a stripe, gapless stripe state with W in cell along one of this direction, right? Instead of a chiral spin liquid. And the competing state is a chiral spin liquid, which is a little bit counterintuition, right? The competing state is a chiral spin liquid, but the ground state is this stripe gapless spin liquid state. For N greater or equal than 6, the ground state again become a chiral spin liquid, and the competing state is also a chiral spin liquid with different background flux, right? With background different flux. The chiral spin liquid is characterized by the mean field saddle point that for each bond, the chiral, the chi parameter, the amplitude is the same, but the first factor is different. It's defined by the amplitude and the emergent flux. So what's the relation between the chiral spin liquid ground state for N greater or equal than 6 on the triangle lattice and the chiral spin liquid for larger N on the square lattice that was described earlier? So we show that so for the triangle lattice, the flux is determined. The chiral spin liquid is calculated by two fluxes, phi up, phi down, right? So the flux here is phi up plus phi down equal to the emergent flux on the square lattice. Yeah. So that the spin-on is gapped by the U1 gauge flux. The chiral, there should be a consignment term if you integrate out the gapped fermion, gapped spin-on. So if you integrate out the gapped fermion, so one can establish a topological quantum field theory with the consignment term, which corresponds to the chiral billion topological order, chiral U1 topological order, and consignment term will generate an ionic statistic for the spin-on. And spin-on is converted to anyons with this fractional statistic angle. There will be gapless edge states carrying the spin degree freedom and supported by the chiral spin as edge mode. And the low energy theory of the edge is SUN level 1 WZW model. Yeah. As Zumino-Witten model, let me summarize. So we find a strong charge fluctuation in the weak model region could further stabilize the exotic quantum phases such as chiral spin, such as spin-on Fermi surface spin liquid with SUN on top of the SUN symmetry. Unlikely mechanism more detectable experimentally to enhance increase the energy gap for the chiral spin liquid. So frustrated lattice is another ingredient that could bring more exoticity with SUN symmetries. Yeah. Thanks very much. Thank you for your attention.